Everyone. Today we are going to go over gravitation, but I first wanted to go through some things on circular motion that I feel like I didn't cover in our last video. And so I just really wanted to make sure that we had covered all the bases. And I also decided to add something that we would usually introduce a little bit later on in the year, but it might be good to start thinking about what the different variables mean. So when we look at circular motion, when you're looking at circular motion, you have a tangential velocity, and your velocity is moving tangent to the circle. And the reason you have acceleration is because that velocity is changing. It's not changing in the magnitude, but it is changing in the direction. And the direction is changing because there's a force directed towards the center of the circle. So our circular path is caused by our force towards the center. So our acceleration is in the direction of our net force. Our centripetal acceleration is towards the center. Then we have our radius. Our radius is from the center of our circle to the edge of our circle. And then our velocity is tangent to that path of motion. Okay, so when we're looking at circular motion versus linear motion, we can really compare a lot of things. And this is the part that I typically introduce a little bit later on in the year, but I'm going to try something a little bit different this time. So when we're looking at position, change in position, and we're looking at that linearly, we're looking at that as a change in x. Our variable is change in x. Well, when we're looking at it in circular motion, that is change in theta, or a change in our angle, okay? And that's measured in radians, okay? And also, when we're looking at what is that equal to, that theta is equal to our arc length divided by our radius. Okay. And then one last thing with that is that when we're looking at our revolutions, okay, when our circle goes through one full revolution, one revolution is the equivalent of 360 degrees. Okay. So 360 degrees is that theta, that angle. Okay. And that's equal to 2 pi radians. Okay. That's what one revolution is equal to. Okay, so when we're looking at time, we're looking at lowercase t, but sometimes you'll hear for circular motion, sometimes we'll use t or sometimes we'll use capital T, which is the same as the period of a revolution. Okay, so frequency would be how frequently a circle goes through. So 1 circle per second or whatever. Whereas your period, it's the period of time for one rotation. Okay. Velocity linearly is change in position over change in time. Okay. And that's measured in meters per second. But when we're looking at circular motion, we're looking at omega. And omega is change in our angular displacement divided by our time. So this is measured in radians per second. Okay. And then finally, when we're looking at acceleration linearly is going to be change in velocity over time. And we measure that in meters per second squared. Well, when we're looking at angular acceleration, that's going to be alpha, and that's going to be change in omega divided by time. And that's measured in radians per second squared. Now, force is a little bit different. Force, we have F, and that's equal to mass times acceleration. Now, when we're looking at circular motion, and we're going to go through this much later, so you don't necessarily have to remember this right now, but our angular or our circular force is going to be called torque, okay? And that's going to actually be equal to our force perpendicular to our distance, okay? Which is also equal to, when we're looking at it in terms of mass times acceleration, it translates to rotational inertia times angular acceleration, okay? And we will talk about that as we go further on in the year. That's not something we're going to cover any more of in this unit. So when we're looking at our kinematics equations, we can go ahead and translate these. So velocity is omega. So omega final equals omega initial plus alpha times time. Okay, change in theta equals omega initial t plus 1/2 alpha t squared. So I'm just translating all of my linear values to a circular value. Okay, here I have omega squared equals omega initial squared plus 2 alpha change in theta. Okay, so you'll see here we have velocity, here we have omega, here we have velocity initial, omega initial, acceleration, alpha, or our angular acceleration, and then time. So I'm just translating our variables. Okay. Now, moving on to another topic that I feel like I didn't discuss last week is this idea of exit ramps. Why are exit ramps on highways banked? Okay. So when we look at that, we look at the reason for that is to increase the centripetal force for the higher exit speed. That is why banked curves are going to be why they're going to be banked, okay? Is to increase the centripetal force for a higher exit speed. Okay? So the normal force can yield a centripetal acceleration. Engineers have learned to bank the curves so that cars can safely travel around the curve without relying on friction at all to supply the centripetal acceleration. And you might be thinking, without relying on friction at all, how is that even possible? And that's what we're going to look at right now. So how many forces are acting on the car, assuming that there's no friction? Well, we have our mass times gravity, so our weight going down, okay? And then we also have our normal force. So our normal force cosine theta, here, because look at our weight is going straight down here and our normal force is coming straight out here. And this is where our theta is. So our normal force cosine theta equals mass times gravity. Also, we have our centripetal force. Our centripetal force is equal to this normal force, this portion of the normal force, and that's equal to sine theta. So mv squared divided by r is equal to normal force sine theta. So we have two values. We have gravity and we have normal force. So we look in our x direction, we look in our y direction. When we sum those, we get mass times acceleration in our x direction. And then here we have nothing because there's no acceleration in this up and down motion, right? There's no acceleration there. So then we look at, okay, normal force sine theta equals mass times centripetal acceleration. So when we're looking for the normal force, we know that the normal force in cosine theta minus mg is equal to 0. So mg over cosine theta equals your normal force. Then we look at our x direction. In our x direction, we noted that our normal force sine theta equals mass times acceleration, which is mv squared divided by r. Okay, so when we go ahead and we substitute in our normal force, which is our mg cosine theta, we get mg cosine theta times sine theta equals mv squared divided by r. Well, sine over cosine is just going to be your tangent. Your masses are going to end up canceling, so you end up getting that tangent theta equals v squared divided by g times r. When we look at that, we realize that your friction really doesn't matter, okay? So we don't rely on friction at all. So what is an angle for a freeway off-ramp curve of a radius 50 meters at a design speed of 50 kilometers per hour, which is 14 meters per second? So what I'm going to do is I'm going to take my radius is 50 meters. That's going to go down right here. My G is 9.8 and my V squared, I'm going to put that right there. Okay. So I'm going to get tan theta equals 14 squared divided by 50 times 9.8. Okay. And then what you would do is take the inverse tan of that to get your theta. So there are some things that I want you to realize. Back in the day, Newton said that the moon is falling towards the earth just as an apple does because they are pulled by the Earth's gravity. Now, when we think about circular motion, what we've learned, we know circular motion is accelerated motion. So why does the moon not crash into the Earth? Well, why is the moon not pulled down towards the center of the Earth? And the reason for that is because the moon is a projectile and it's constantly falling towards Earth, but it's falling at a curvature that's going to cause it to go around the Earth. So it's going to circle the Earth. The moon does not hit the Earth because it has a large enough tangential velocity to keep it in circular motion. So you need to have a large enough tangential velocity to keep you in circular motion. Now, the other thing that we need to look at is gravitational attraction. Now, gravitational attraction is going to be diluted by distance, meaning the further an object gets away from the center of the Earth, the less that gravitational force is going to act on it. So when we look at gravity and vector fields, a vector field gives as a function of position and perhaps time the value of a physical quantity that is described by a vector. So vector fields are represented by field vectors indicating direction and magnitude. So when you look at these vectors, you can see that they're indicating direction, okay? But then magnitude, you can see magnitude based on how close they are, okay? So your lines are going to be closer together here, and they're getting further apart here as you're moving away, okay? When more than one source object with a mass or electric charge is present, the field value can be determined by vector addition. Conversely, a known vector field can be used to make inferences about the number, relative size, and location of the sources. So when we're looking at our forces, the main force that we're going to look at right now is this gravitational force. Okay, so nature is split into four fundamental forces: gravitational force, electromagnetic force, weak interaction, and strong interaction. Now, weak force and strong force, this is dealing with atomic structure and keeping atoms together, okay? That's dealing with atomic structure, and it's really strong, and it's got to be very strong in order to keep atoms together. And if you think about it in terms of, so the center of your nucleus is protons and neutrons, so positive, and then you've got electrons on the outside. What causes that from crashing in, or what causes the protons together, to stay together, okay? And that's dealing with these forces. Then we have your gravitational force and your electromagnetic force. We're not going to look at our electromagnetic force right now. We're just going to look at our gravitational force. Now, the law of gravitation states that there is this G value, a constant value that scientists have learned and they've measured, times the mass of object 1 times the mass of object 2 divided by the distance between the center of their masses squared. That equals the gravitational force. So there's actually technically a gravitational force between you and any object next to you. Now you have to think though, what are the masses of those objects? They're not very big. But when we're looking at the Earth is extremely massive. So we're looking at a really high mass here, okay? And so that's going to help us determine the force of gravity. Gravity is universal. Everything pulls on everything else in the universe based on mass and distance, okay? And that's why this is called the universal law of gravitation, or the law of universal gravitation. Universal gravitation constant is your G value, and that's equal to 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. And it is a constant that scientists have determined based on experimental design and experimental discovery. Okay, that is something that's really important for you to realize. Another thing I'd like for you to realize is this value right here that says times 10 to the negative 11. That actually indicates that gravitational force, while we feel gravitational force a lot, it still is a very small force. It's not as strong as other forces. So looking at the universal law of gravitation, which I will go ahead and write that back up over here, gravitational force is equal to G times the mass of object 1 times the mass of object 2 divided by D, or sometimes you see R squared. The farther objects are from each other, the less force between them. So if you look at this, if I double the distance, well, what happens? Well, if I double that distance, I end up getting G times M1 times M2 divided by 2D, and I square that. So now what I've done is I've pulled out that 1/4, and then I have the same value as my force of gravity. So I've cut that force by 1/4 by doubling the distance. What if I triple the distance? Okay, again, I have G m1 m2 divided by 3d squared, which ends up giving me 1/9 times my force of gravity. Okay, if the distance is cut in half, what happens to the force? Okay, well, let's try that again. G times m1 times m2 divided by 1/2 d squared. Well, that's going to be 1 divided by 1/4 FG. And whenever you divide by a fraction, you multiply by the reciprocal. So you really end up getting 4 times the force of gravity. So if you bring things closer together, the force gets stronger. Now let's talk about that in terms of something that you're aware of and familiar with. What if you had 2 strong magnets? If I bring those strong magnets together, the closer they get together, you can feel those magnets pulling on each other very strongly, okay? The farther they get apart, you don't feel them pulling on each other as strongly, right? So the closer they are, the more force you experience. The farther apart, the less force you experience. And then also, if I double the mass, I'm going to double the force. If I double both of the masses, I'm going to quadruple the force. So the biggest thing that you need to understand is what happens as you change the mass, or what happens as you change the distance. It's not about what are the numbers, what is the actual value. It's really more about what's the relationship between increasing or decreasing mass and increasing or decreasing distance. The force of gravity is the weakest of the 4 fundamental forces, though, and that's what we just talked about. Now, this might be helpful for you to go ahead and write down that the mass of Earth is 5.98 times 10 to the 24th kilograms. And the reason that might be helpful for you to write down is because when you're doing the problems for your assignments, then maybe that will help you so you don't have to keep looking that up. But these values are also given in the front cover of your Giancoli book. So gravity. Gravity can change as altitude changes, and we know that. And we know that gravity is a force. So the sum of force is equal to mass times g, and g is a value that we have from acceleration due to gravity on Earth. And that's equal to gravitational constant times the mass of the object times the mass of the Earth divided by r squared. So let's look at a sample problem. Use Newton's law of gravitation to find the force of gravity acting on a 1,000 kilogram filing cabinet at sea level. Okay, so we're going to need to know a couple of values here. Okay, we're going to need to know so we have force of gravity is equal to G times M1 times M2 divided by D squared. So G is a value that we were given as a constant, 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. Then I have mass 1. My mass 1 is 100 kilograms times my mass 2. I need to figure out what the mass of the Earth is. And we just talked about what the mass of the Earth is. 5.98 times 10 to the 24 kilograms. Okay. Divided by 6.38 times 10 to the 6. That's going to be meters, because that right there is the radius of the Earth. And someone might say, well, where the heck did you get that? I have that as a standard, but I have it written down on my piece of paper, but you can find that in the center or in the front cover of your textbook, your Giancoli textbook. And that value is squared because of this D squared over here. So the next thing I'm going to do, just to double check my math, is notice that my kilograms squared cancels and my meters squared is going to end up canceling. And that's going to end up giving me 980 newtons. So the next thing it says, what force of gravitational attraction is the cabinet exerting on the Earth? So we just figured out what the force of the Earth is on the cabinet. Now we're looking at what's the cabinet on the Earth. Well, that's going to be 980 newtons. And that's going to be 980 newtons because of Newton's third law. So satellites. When we're talking about satellites, satellites are moving around the Earth or whatever object they're moving around. Okay. And so a satellite is an object orbiting the Earth because it has enough velocity. To complete a complete circle will be formed if the takeoff speed is 27,000 kilometers per hour. So if you got a plane or you got a rocket that would go 27,000 kilometers per hour, it's going to get to orbit the Earth. Okay. But really, what a satellite is it's a projectile that's falling towards the Earth. But as it falls towards the Earth, it just follows the curvature of the Earth. Okay. Weightlessness occurs when objects are accelerating as in free fall. Okay. So when we're looking at our satellites, something that's really important is that there's a centripetal force, and the identity of that centripetal force is going to be equal to the gravitation. So for a satellite orbiting an object, you have mv squared divided by r equals g times m1 times m2 divided by r squared. So in our next question, we're talking about satellites. A 1,200 kilogram satellite is set into circular orbit at 1,500 kilometers above the surface of the Earth. Find the orbital speed of that satellite. So like we just said, our sum of forces is centripetal, and so that's mv squared divided by r. Our sum of forces, our centripetal forces, is equal to our gravitational force. That's what's causing that centripetal force. So we end up getting mv squared divided by r, and that's the m of the satellite, is equal to g times m of the satellite times m of the Earth divided by r squared. So my masses ended up canceling. Also, one of my radii ends up canceling, which is kind of nice. So we end up getting v squared equals g times me divided by r. So we end up getting velocity is equal to the square root of g times me divided by r. And now we need to figure out what are our values. Well, we know that our g is equal to 6.67 times 10 to the negative 11. We know that the mass of our Earth is 5.98 times 10 to the 24 kilograms. And then we know that our radius is 6.38 times 10 to the 6 plus the 1,500 kilometers, which is going to end up giving me 1.5 times 10 to the 6 meters. Okay, because I needed to convert that to meters because the distance that I have here, or also what my g value is in meters. And I end up getting that my velocity is 7,115 meters per second. Okay. What is the period of orbit for that satellite? Okay. Well, so this is what I need to look at. What is the period of orbit? Well, we have a velocity, and our velocity is change in displacement or distance divided by time. So what is the distance that an object travels when it goes in one full orbit? Well, that's going to be 2 pi r divided by t, which is the period. So we're solving for period. So we end up getting, when we manipulate this equation, I bring t to one side and I bring my velocity to the other side, 2 pi r divided by v. So I get 2 pi times r, and my r value is going to be 6.38 plus 1.5 times 10 to the 6 value, okay, divided by 7,115. Okay. And so when you go ahead and plug those in, you should end up getting your value there. So Kepler's laws, all planets orbit the sun in an elliptical path. So in your textbook, you're going to go through Kepler's laws, and you're just supposed to know what Kepler's laws state and what that means. So we know that the planets are orbiting in an elliptical path. A planet is going to cover equal amount of space in equal amount of time. That is super important. Equal amount of space in equal amount of time. Okay, so when it sweeps through one side of, say, the Earth sweeps through one side of the sun, it's going to cover the same amount of space on that side as if it would on the other in the same amount of time. The ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their mean distance from the sun. Okay, so we have T1 squared divided by T2 squared. That's the period of the distances, or the period of the squares of the periods of time, is equal to the distances cubed ratio. Okay, and so that's going to be one of the main Kepler's laws as well that you're going to need to do. So what I recommend for you is to read through that section briefly in your Giancoli textbook, just so that you're familiar about what Kepler's laws state. They're not tested in terms of numerical values in AP Physics 1, but they are tested in terms of conceptual values. Okay, so if you have any questions, please go ahead and reach out.